Good morning. So we are solving this numerical on stresses in beams. This numerical is basically a numerical which has actually two numericals inside it. So there are two parts here. So up to the second line is one part, and what you get in the first two lines is used as the input for the third and the fourth line. Okay. Now if you observe here, here, out of this equation, m by I is equal to sigma b by y. Okay, what and all we have in this? It says it is a cast iron beam and it's a simply supported beam. So let me write it as like this: a cast iron beam simply supported like this. Okay, and its section. Now at the end, I will try to draw the section here. This is 20 mm into 20 mm. 20 mm into 20 mm section. So here I draw like a line, but at the end it looks like a square. Okay, and then a cast iron. This is, see, I think it is a data which is not required for us. Whether it's cast iron or mild steel, we really don't matter. We are just worried about the numbers here. Okay, a cast iron test beam. It says it is a test beam. So that means you are trying to find out of this test beam because it fails finally. It is not a beam to be used for some used later. It is a sacrificial beam which is used for testing and finding out the stress, maximum stress. It is actually a test beam and its dimension is breadth is 20 mm, height is 20 mm. So since B and D are equal, no issues. And it is 1 meter long. This is 1 meter long and it is simply supported, which are shown now at the ends. It is simply supported at the ends, and here it's comma. Fails when a concentrated, that's point load of 640 Newton is applied. So that means when you apply 640 Newtons of load, it fails. So that means the material yields. So that means it doesn't start taking too much of load, so it starts bending too much. So that is when it fails. So they are given this data. Out of this, we need to find out what here. We know that out of this we can find out m, because we know for simply supported beam what is the maximum bending moment, and we can find out I because BDQ by 12 is known. We can find out y because y is d by 2, and we can substitute all this directly here. And what is not known to be sigma b. When the sigma b is found out from the first two lines, then the sigma b value, because it says what UDL will break a cantilever of the same material. So that means here whatever the material was used in the test beam, same material is used here. So that means the stress at which the material fails is same. So with this stress, whatever you have found out, what UDL it can take for a cantilever. Okay, and the arrangement is different. So whatever the answer that you find in the first two lines will be used to find out sigma b, and that's in the second part of the problem. Sigma b will be given, and here they are given 50 mm wide and 100 mm deep, so they know I and y, so they will find out m, where for m it says what UDL will break a cantilever of the same material for a. So that means for a cantilever, for a UDL, what is Mmax? For a cantilever, for UDL, with UDL. WL square by 2. So you need to substitute this WL square by 2. Here L is known because it says it is 2 meter long in that WL square. Okay, only W is not known. What does that W give? W will give you what UDL it has now. So that will give you W. So it is just simply playing with the same equation. It is just simply playing with the same equation. In the first part of that is in the first two lines, you find out sigma b, and for the second two lines, sigma b is found out. Then you know I and y. Then you find out m, which is ulta. Okay. So we'll start solving the problem now. Okay. So now we know that by using this equation here, So M by I is equal to sigma B by Y. So we're supposed to find M, we're supposed to find I and Y. So let us find out. So what we want here is sigma B. Guys, for a simply supported beam with a point load. So what is the bending moment, guys? Now what is the bending moment? You draw it like this, no? You draw it, please look to the previous diagram. It looks like this. What is the value of this? Basically, Mmax is how much? Mmax is, suppose if this is P, suppose if this is, instead of 640, if you call it as P, then this is P by 2. P by 2 into L by 2. So P by 2 into L by 2 is PL by 4. So even in the examination, if you forget those equations, you can come back and conceptualize this and then write PL by 4. This is where you will have the maximum bending moment. It is where it fails. Last time we said that if you want to break a stick, you hold the stick like this and break like this. So that means you are holding at these 2 points, and this knee is used as one more point and it breaks here. So this is where maximum bending moment is. It is where it breaks. So that value is PL by 4, where P is nothing but 640 newtons. So here, what we do? We find out M. M is equal to PL by 4. So P is how much? 640 newtons. And what is L? 1 meter. So L is 1 meter. L is 1 meter divided by 4. So what's the answer, guys? 160 Newton meter. So 160 Newton meter is the answer. Okay, once you have found out M, right now you have found out M. Now you are supposed to find I. What is I for this type of beams? So I is equal to BDQ by 12. D is 20 mm. Okay, so guys, if you want this, you can write it as 160 into 10 to the power of 3 Newton millimeter. So meter could be converted as 1000 millimeter. So you can write like this because others are in mm. Finally, it's left to you when you are using this equation. So B is 20 mm. D is how much, guys? D is also 20 mm. Breadth and depth are same. 20 mm to the power of cube divided by 12. What's the answer, guys, here? 666.6 into 10 to the power of, that's the answer, 666 only. 666 mm to the power of 4 is the answer. Okay, and then we'll come back here. So now we'll go to this. Is it visible here? Up to here. Okay, now I know y. Y is nothing but d by 2. So we know that here, guys, in this beam, this will be the neutral axis. Suppose if it is the beam, all these points starting from this point are neutral axis, and these fibers at the extreme, will have the highest stress. Last time we showed this is maximum stress, this is maximum stress. At some point here, where it is called the neutral axis, there is no stress. But at the extreme, either like this or like this, I mean here or here, there is maximum stress. Suppose if it fails, where does it fail? It fails at a distance of d by 2. This is d, guys. This is d. This is depth d. So from the neutral axis, here it is compression, here it is tension. Both are stress only, compressive stress or tensile stress. So it may fail here or here. Okay. And this y refers to, guys, may I sing for you? This is stress for the fiber stress for the fiber which is at a distance y from the neutral axis. If you want the stress at a distance which is at this, then you'll get this stress. So what is this distance? This is d by 2 because this whole distance is d by 2. So you should substitute this value here, d by 2, then you get the stress at d by 2 distance. If you substitute y as 0, then you get the stress at neutral axis, which is 0. Okay, so y is equal to d by 2. How much is depth again? Basically, depth refers to full depth of the beam, that is 20. Don't make small mistakes. So 20 m divided by 2, that is 10 mm. So from the neutral axis, since the whole depth is 20 mm, from here to here, depth becomes half from the neutral axis. Okay, from the neutral axis. So now we substitute all this here. What man? How much is this? 13,333.33 m to the power of 4. Okay. So please make these corrections and please be good with calculators, because even if you are writing this right and then if you go wrong, then nobody knows where you've gone wrong. So they would give you this much. So please be good with calculator. So please practice. Okay. Now I'm substituting this. Okay. Now I'm now using the same equation here. M. What is M, man? 160 into 10 to the power of 3 Newton millimeter. Okay, which is equal to sigma B. Sigma B is not known to me, so that I have to find out. And what is I? The 13,333.33 millimeter to the power of 4, and here y is equal to 10 mm. So from this equation, I will try to find out sigma B. Sigma B is equal to 160 into 10 to the power of 3 Newton millimeter into 10 mm multiplied by 1333.33 millimeter to the power of 4. Okay, so here this mm, it becomes mm square. That mm square cancels this with this, right? No? So what is left here? Basically, what is left? Newton is left, mm square is left. The answer is Newton per mm square. Newton per mm square, because it is in the denominator. It's in the denominator. So Newton above denominator mm square. So it is the unit of stress. So the answer, the formula is right. Okay. So sigma B is how much, Mice? 120. 120 is less than like 250 or 500. So it's a very safe stress for this. Yeah, it is a safe stress, but it has broken at 120 itself. Maybe it is not steel, maybe it is something like aluminum or something. Okay, 120 Newton per mm square. 120 Newton per mm square is the bending stress of this material. Basically it is actually a test beam. That test beam has got a bending stress of 120 Newton per mm square. So this is the first part of the problem. And now, once I have found out this, then I move to the second part of the problem. What I do? I got this answer from the test beam that the maximum stress this beam can take, the material can take is 120. Now I go to the second part of the problem. Okay? Second part of the problem is, what UDL will break a cantilever of the same material? So I'll first draw a cantilever here. Okay, and this cantilever is carrying what? UDL. This cantilever is carrying UDL. It's carrying UDL, and this is of the same material. So now the material is same means what? Now what does this understand? Material is same means what? Bending stress is same. So sigma B is equal to 120 Newton per mm square. Bending stress is, so please read every word and what is. Now the question has a lot of data in it. Now should know what data is, should not miss. It is a what UDL, it is a UDL, will break a cantilever, it's a cantilever of the same material so that means sigma b is 120. Every word has got a data in the numerical, so don't miss it. Please be careful. And it continues 50 mm wide. 50 mm wide. 50 mm wide means this beam, if you look at from the sides, this width is 50 mm. And what is the height? Now what is the depth? Depth is 100. Depth is 100 mm. And how long it is? How long the beam is? This is 2 meters. 2 meters. Guys, what they are asking is, here is a cantilever. They want you to place a UDL, maybe like a sack of rice throughout. Okay? And here they are asking, W is the uniformly distributed load. Usually the units are kilonewton per meter. It's left to you because here it is millimeter. You can actually finally convert that into kilonewton per meter. And this is actually for small loads. Usually the loads would be like 640 kilonewton or 100 kilonewton. Here the load applied are very small because these are small sections. 20 mm into 20. How much is 20 into 20? This much. 2 centimeters. Very small beam. They are playing with very small beams. So here this is 100 mm. This is 50 mm. Of course, here the beam is quite big. 100 mm means almost up to this size beam. Okay, you want to place UDL. So they are asking, what is this? Once you have done this, okay, very similar to the last time. Where does the beam fail when you start increasing the intensity of UDL? Whether it fail, no. Will it fail here? It will fail here by common sense. So you know that if you try to draw bending moment diagram, so the bending moment diagram will come like this. Bending moment diagram will come like this, and here you will have the maximum bending moment. What is Mmax for a cantilever with UDL? Now what is the formula? W L square by 2. Now how did you get it? Basically, so whole of this UDL, W into L, placed at this point. So that is W into L. And this can be imagined to be acting at L by 2 distance. So this is basically W into L by 2. You got it as W L square by 2. If you forget this formula or in the examination you have a doubt, okay, I'm not sure about this equation, then you can imagine bending moment will be maximum at this point. The whole UDL can be imagined to be placed in the center. So that says, UDL unit says it is so much kilonewtons for every meter. It is 2 meters. So whole UDL means so much of kilonewton. For every meter it is so much. For 2 meters it is this into 2. This whole UDL placed at this center of the UDL. So this whole length is 2 meters. And half of this is L by 2. So it is W L into L by 2. It is W L square by 2. So please, if you happen to forget this equation, please go back to SMD, BMD concepts and then find out this. Okay. So Mmax is W L square by 2. So in this numerical, sigma B would be given, Y would be given, and I would be given in the second part of the problem. You are supposed to find out M. In this M, what they are supposed to find? What UDL. So that means they want you to find this W. Okay. So let us now substitute these values here. So here we have found out that sigma B is 120 Newton per mm square. So I have written this here. Sigma B is 120 Newton per mm square. I will write this here and erase this. And this is what we have found out. And now go for the second part of the problem. What UDL will break? So I'll use the same formula. M by I is equal to sigma B by Y. So if you use this equation here, so M is equal to W L square by 2 is equal to sigma B. So what is sigma B, guys, here? 120 Newton per mm square. And then what is I for this? What is I formula? I is equal to BD cube by 12. So B is how much? 50, and D is how much? 100 mm cube divided by 12. So what is the answer? 416, 5 times. 416,666.6 millimeter to the power of 4. Okay. I is known. So I is known here. So I is 41. So 4165 times 0.66 millimeter to the power of 4. And then here, what is y? What is y? So neutral axis is this, and these fibers usually fail because of the extreme stretching. So y should be always taken for the extreme fiber, which is d by 2. How much is d here? Sorry, how much is d by 2? 50. So 50 mm. 50 mm. So here in this equation, everything is known except W. And what is L? What is L? So you know L is nothing but 2 meters. So W into L, which is 2 meters square divided by 2. So substitute this. So put everything in order and only find out W. So if you want W, everything has to be pushed to the other sides. So it becomes 120 Newton per mm square into this big number 41. So 66 millimeter to the power of 4. And then here this 2 goes above. And then this is 50 mm, and this 2 meters square comes below. Guys, please cancel out the units. Guys, here one thing is wrong here. I think everything is in mm square, so this is in meters. So please convert this into millimeters. You can be completely wrong. See what? Okay, how is that I found out? Because I was finding everything in millimeter here, and I wanted to cancel this out, but I'm finding this in meters. So this is 2 meters. 2 meters is 2 into 10 to the power of 3 millimeter. So substitute this. So here basically this has to be doubled, squared as per this, it is L square. So don't go wrong. Why in numerical, if you get good marks, people say you're good because you're extra cautious in everything. So this equation becomes finally, so I can substitute this into as 2 into 10 to the power of 3 or 2000 mm. I can simply write this as 2000 mm square. So here mm square. So here this mm square and this cancels out. Here this mm square and this mm square also cancels out. And what is left is, now what is left, man? In the whole of units, what is left? Newton is left and divided by mm is left. So that means basically we are trying to find this. How many, that's in Newton, how many newtons of load for every meter or millimeter? That is the intensity. Okay, we get that. Same unit. Yes, Panto. How much you get this? Huh? Point? 4.99. Okay, everybody is getting the same answer? 4.99 Newton per mm. Ashtana? Or is it actually kilonewton? 4.99 per millimeter. Okay, 4.99 per millimeter. So, W is equal to 4.99 Newton per millimeter. Guys, if it is 4.99 per millimeter, so much would be the UDL for meter? If it is for mm, it is 4.9. For meter, what will be the load? If you expand the same load for 1 meter, then what will be the load? 4.99 into 10 to the power of 3. So that means the same load for 1 mm, suppose if you keep adding the same load for 1 meter, it becomes 4.99 into. So basically what you are trying to do is that you want this, so you want to multiply this above and below by 10 to the power of 3. 4.99 into 10 to the power of 3 newtons divided by this mm, no? You make it as 10 to the power of 3 millimeter. So much is actually 10 to the power of 3 millimeter? 1 meter. So this is 1 meter. This is 1 meter. So finally this becomes 4.99 kilonewton meter. If you want in this pattern of unit, we get this like this. W is equal to 4.99. Is it visible, guys? Here? 4.99 kilonewton per meter. So you can write this as it's almost like 4.99. So, or otherwise you could now you could almost approximate it to 5 Newton per mm. Here you can call it as 5 kilonewton per mm. It's left to you. Guys, this is actually 4.9999 it will come. You could have made it as 5 Newton per mm, and here also you could have made it as 5 Newtons. So this is how you solve the problem. This problem has basically 2 parts of the problem. So this could be definitely easily given for 10 marks because there is so much of calculations in it.